Hi there, I'm Steve Reynolds. I'm a professor in the School of Earth and Space Exploration at Arizona State University. Thanks for joining me on this field trip. The goal of the field trip is to try to show you a little bit about the Cenozoic geology of the Phoenix area with two main stops, one here in the South Mountains, which is the range south of Phoenix, and one in Papago Park, which is kind of north of the Arizona State campus and a little bit to the east of Phoenix. We'll start here in the South Mountains because it really is the thing that drove the geologic evolution of the region. If you look at the range behind me, there are two main components. Off in this direction, the dark rocks on the ridge crest are Precambrian metamorphic rocks. From the pass over to the east are granitic rocks, including a granite and a granodiorite. Those rocks have been dated by uranium-lead zircon ages at 20 million. If you look at the Precambrian rocks, one of the things you'll notice is they have some ledges that are inclined off to the southwest. We're looking south. And what those ledges are, those are shear zones within the Precambrian metamorphic rocks. And in cross-section, it looks like this. Unfortunately, the cross-section is looking from the other side of the mountain here, but what you see is a contact between the granite, which is this way, and the Precambrian metamorphic rocks, which are that way, so it's like that. And then you can see that I've shown these little dashed lines in the Precambrian rocks. Those are the shear zones. The other thing that you see in the granitic rocks is as you're down low in the range, those rocks are undeformed, and as you go up, they become more and more myelinitically deformed, more sheared, lots of foliation, lineation, and we'll look in detail at some of those rocks. And this shear zone in the granitic rocks projects over the pass and into these shear zones back in here. So in this particular place, we'll do two main stops. We'll go look at the contact between the metamorphic rocks and the granitic rocks, and then we'll go up and look at these just spectacularly sheared rocks in the granodiorite and the granites up on top of the range. A good place to start in the South Mountains is the contact between the granite and the metamorphic rocks. So we're in a part here where the granite is a very light colored rock. It's got some very nice fracture patterns, which we'll look at in a second. And then the metamorphic rocks are there. And this contact in this particular place is a little bit faulted, but overall it's a nice intrusive contact with dikes of the granite going into the metamorphic rocks. Clearly the granite is the younger of the two. So let's walk over here and look at the metamorphic rocks. So what you can see is the rocks have a light and dark banding. It's a gneiss, and most of the light colored components in here are related to the Precambrian metamorphism that made this rock. In some cases, some of the thinner light colored things are actually dikes related to the granite nearby. The other thing you can see in this exposure here is there are shear zones cutting this rock. So there's a metamorphic layering, which you probably can't see from there, but what you can see are these later shear zones that are cutting across that metamorphic fabric. And these are the shear zones that I pointed out below. Some of these shear zones have this sense of shear, and some of the shear zones have the opposite sense of shear. The ones that have the opposite sense of shear, top to the southwest, are typically steeper. And the idea in here is there was first a shearing event like this, and then there was a doming event, and you sheared the other way during that doming event. Where we are on this cross section is right at this contact here. Remember, the cross section is drawn from looking at the other direction. So the dark rocks are those, and the granitic rocks are these. This is what the granite looks like. It's a medium grain rock. It's a little bit stained from some sulfide minerals that were in some of the fractures. But one of the things to look at in here is that these fractures have a pretty clear orientation. And the fractures is actually one of the reasons why I started studying this range. I had worked with a guy, and we had been studying the fracture orientations in granites of different age. And when we came to this place, we said, this looks like this is a really young rock, like 20 million, 25 million, based on the fracture orientations. But this rock, as you take it up in elevation, becomes sheared into a metamorphic rock. And so that implied that there was a post 25 million year old metamorphism in here, which was unheard of any place in the western US. So I said, I think I should come in here and study this. And so I did geochronology on this rock to figure out how old it was, did the structural studies, and we demonstrated that the shearing in here was actually younger than 25 million. It was, 20-ish, 20, 19, 18, something like that. And it was largely because of these fracture orientations. This kind of fractures, which we call joints, are controlled by the orientation of the stresses. They essentially have to open up against the stresses, and so they like to open up in the direction that it's easiest to push, which means there's the least stress coming in that direction. And so these fractures really are telling you something about the stress orientations when this granite came in. And the fact that these have these sulfide minerals along it means that those fractures developed while the granite was still hot and there were still hot fluids around. As a reminder, we're in this rock right here, right next to the contact. Remember, the contact's drawn in the other direction. This stop, we're at the top of the range at a place called Dobbin's Lookout. And what we have exposed here are the granitic rocks, in this case a granodiorite, has been sheared, and here's the sheared fabric in the rock. So what you're seeing in this particular face is the foliation like this, and it has a lineation, which you can't see there, but we'll show it to you, is like this. And in this particular case, these rocks it's a really clear sense of shear that you can interpret from them, and it's top to the northeast. So in these particular rocks, they were sheared this way. They've been tilted back a little bit by this doming, but they were originally sheared like that. And you could either think, well, the top was sheared like that, or you could think that the bottom was pulled like this. Either way. So let's talk a little bit about how we think this might have formed. We envisioned that the South Mountains shearing happened along a shear zone that was inclined towards the northeast. This is northeast, this is southwest. And up above the brittle ductile transition, you would have had fracturing and formation of fault rocks. Below the brittle ductile transition, you have shearing under ductile conditions. So you make this foliated texture, you make the lineation. This type of a fabric we call a myelinitic fabric. It's formed by recrystallization of quartz, and the rock is just shearing. It's still solid, not molten, but it's soft, and so you can shear it. And so you start by, I think the easiest way is to pull this, I think the easiest way to envision this is to think of the rocks in the South Mountains being pulled out from underneath the rocks to the northeast. You could say, well, these rocks slid off the top, but this fault goes all the way under the Colorado Plateau in the transition zone, so it was like North America slid off the South Mountains, or not. So the easiest way to think of this is the rocks in the South Mountains were pulled out from underneath it. So that's one, and of course this cross-section is drawn looking from the other direction again, sorry. And so what happens with time is you bring these rocks that were ductily sheared and you bring them up to shallower levels, and they get overprinted by fracturing, and you start making fault rocks and shattered breccias and things like that. And then the other thing that happens in here is you can see you have this tapered wedge of the upper plate, and it's not going to have much strength because it's getting thinner and thinner as it goes towards this area. And so that is the area that breaks up into a whole series of tilted fault blocks. And we will revisit those later. And then finally what you end up with is this scenario where the myelinitic rocks are exposed at the surface, so you are here, and you have all these tilted fault blocks off to the northeast from us, between us and ASU. And but you've essentially brought rocks that started at 10 kilometers or so and have been brought up along this shear zone and this detachment fault and brought up to the surface. The term detachment fault, we use it for a gently dipping normal fault that is sub-regional to regional in extent. These things mostly have on the order of 30, 40, 50, 60, 70 kilometers of displacement on them. So they're really big normal faults. And they operate at a low angle. They form at a low angle. Some parts of them are steeper, but fundamentally they're low angle normal faults. This close-up shows the lineation in these rocks, trending northeast in that direction, southwest in this direction. All of these rocks. This is a view of the foliation sitting like this, and the foliation has features in it, like these things, that help us determine that the census shear is like this. So this side's going this way and this side's going this way. That's the northeast, so that's a top to the northeast. But if you look at closely, you can see some of these interesting little features that tell us the census shear. One of the really interesting things in the South Mountains are these dark gray to black veins. When you look at these with high-powered microscopes, you can see that they used to be glass, and some of them still are glass. These features are called pseudotacholites, and they're interpreted to be melting of the rock. In this case, it's melting during an earthquake. So you had a seismic event, clearly on a very low angle fault in here, and that seismic event generated enough friction to melt the rocks. So take your hands, put them together, and rub them, and you get some amount of heat. Press hard together on your hands and rub them, and you get more heat. So if you're at some depth and you have a fault move, you generate more frictional heat, and so you can melt the rock easier. And so these are interpreted to be fossil earthquakes, and along structures that you can see are very low angle. So, some people say, oh, low angle faults don't generate earthquakes. These generate earthquakes, and other people besides me have studied these in even more detail and come to the same conclusion. An important component of the mid-Cenozoic evolution of the Phoenix area is Papago Park, which we're in now. As hopefully you can see in the butte behind me, the rocks are layered and tilted. The dip is towards the southwest. What you can't see in here, there's a whole series of faults that have repeated that section and again and again. So you have a section here, a fault dipping to the northeast, another section, another fault dipping to the northeast, and another section. And so there's some repetition in here by normal fault. The other thing you can see in these rocks is they have these pronounced holes in it. It's called Tafoni weathering, and it's a weathering phenomena. They're mostly horizontal, though they've developed when the rocks were already tilted up fairly close to the surface or on the surface, and things like water accumulates in there and it kind of rots the rock, and that material gets washed out, and so the holes get bigger with time. The key rock unit in Papago Park is this unit that forms the main buttes. So take a look at this unit for a second and just make some observations about what you see, and then we'll look at it. So let's interpret what this rock tells us about the environment when this was deposited. Approximately 20 to 25 million years ago. Clearly there was high relief, there was a mountain that was contributing these angular clasts. It was probably steep. The clasts don't look like they were weathered very much, and so maybe it was dry like it is today in Phoenix. So those are some observations you can make, some interpretations. The other thing is you can tell what that mountain range had in it. It had meteorite and it had granite, and it pretty much had nothing else. And So you'd say, well, why aren't there Paleozoic rocks here? Things like that. Well, by 25 million years ago, when this rock was deposited, this whole region had been uplifted, and all of the Paleozoic rocks that are exposed in the Grand Canyon were eroded off of this. So those rocks just weren't around. You had Precambrian basement rocks sitting at the surface. Notice there are also no volcanics in here, and that tells you that this is a pre-volcanic rock. Not very far in that direction is the Superstition Mountains, which has abundant volcanics. If this rock was deposited after those, you would see some of those clasts in this material, and you don't see it. And there's no volcanic ash, there's none of that. So this is a pre-volcanic rock. The volcanism started about 22 in this area. So that's why I say this is probably a 20 to 25 million year old rock. As far as depositional environment, the matrix of most of this stuff looks like red mud. And so a really reasonable interpretation is that this was all deposited as debris flows, and the debris flows and the mud matrix allowed that material, that fluid material, to carry such big clasts because you had some buoyancy from the actual mud. So let's talk about the context that we think these rocks were deposited in. We noticed that there were some normal faults in Papago Park. And so what we think happened is you started to break up the land surface with these normal faults. You made mountains in the corners of the blocks that were tipped up. These are rotating fault blocks. And you make basins in the corners of the blocks that are rotated down. Material could be derived from the mountain and the fault scarp and go into the basin. It could also be derived from this up-tilted corner of the block that it's resting on. And so we think that both of those are contributing to this type of basin environment. Notice also I have some big landslide blocks in here. We're going to show you one of those just around the corner. And we think that those landslide blocks could come off the fault scarp, but maybe they're more likely to be derived from this tilted fault block. As you take the block and you tilt it, at some point you oversteep in it, and so you get a rock slide that then turns into either a debris avalanche or stays as a rock slide. And those rocks end up being intercalated in the rest of the basin. Let's talk a little bit about the societal relevance of this. We're up in this area right here, and out in this area, a major electronics firm dumped 100,000 gallons of trichloroethylene down a dry well. And Doug Bartlett and Julia Johnson and I studied this geology in here in the subsurface mostly with drill holes. There was some geophysics, wasn't very good, frankly. Because you're trying to collect geophysics on busy city streets, so it just didn't work. And so what we found is that there were these buried ridges in here, and these buried ridges were blocking the flow of TCE and keeping it in this area where you could remediate it, as opposed to going all the way down to downtown. There's some more TCE downtown, but there were some other operations here by the airport, and they likely contributed a lot of that TCE that went to downtown Phoenix. So northeast dipping, normal faults, southwest dipping layers, repeated again and again. We could drill through this and see this, and then from that understand how the groundwater was flowing, how it might have flown in the past, where the TCE might go in the future. I'm lucky enough to teach at Arizona State University, which is located here, and this section of rocks starts at ASU and is exposed on both sides of the Salt River to where we are in here. So we can actually bring students in here to study this whole transition. And it starts out with these coarse debris flow deposits like this, and then there's kind of more clear water conglomerates, alluvial fan stream deposits, things like that. And then there are finer grained rocks that are sandstones, siltstones with mud cracks, and more likely deposited in the floodplain of a larger river system. And then it's capped by some of the volcanics. The volcanics are poorly dated because they've been altered by potassium-rich fluids. And so if you're using the potassium-argon or the argon-argon method of trying to date these rocks, you're really dating the age of the alteration, not the age of the volcanic rock. So these rocks are likely to be 18, 19, 20 million, but poorly dated. The last piece of context we need is to relate this to the South Mountains, which are that way from us here. So we're in one of these tilted fault blocks, and
the interpretation is that these tilted fault blocks were essentially broken up as these rocks were displaced off the top of the South Mountains, or as the South Mountains were pulled out from underneath them, whichever way you want to refer to that. And so there's a detachment fault between these rocks and the South Mountains. We think that that detachment fault has on the order of 30 or 40 kilometers of horizontal displacement. These rocks look like they were about 10 kilometers deep, and that fault has about a 10 or 15 degree dip based on exposures in the actual outcrop and a seismic line that an oil company ran along here a long time ago. And so if you just do that trig, you get something like 30 or 40 kilometers. Could be more. This rock is a granite. It has quartz, it has feldspar, it has dark minerals, which in this case are mostly biotite, which have been slightly altered to chlorite. And it's angular, pretty large. There are larger ones, but that's what you get. Right next to it is this rock, which you can see a metamorphic foliation in it. This is one of the metavolcanics that's been silicified, so it looks like a quartzite, but it's actually a metavolcanic. This rock has angular clasts, and it has a matrix that you can see looks like mud and sand. And so the easiest interpretation for these is that this is a debris flow deposit, and the matrix of mud helped the clasts be carried because it helps with the buoyancy of keeping them up off the stream bed. This is another component of the rocks in Papago Park. It looks mostly like it's granite. It has a fragmental character, but the matrix in a lot of places looks like, some of it's red, but in a lot of places it looks like it's just crushed granite. And it looks like these pieces have just kind of been pulled apart a bit. Whereas this has a mix of different clasts, and the clasts have clearly been moved around and jumbled, and so you have more variability. There are parts of this rock that are 10 meters across and essentially unbroken granite. So our interpretation of this rock is that it's a landslide deposit in these red beds. And so, some very steep topography, and this thing came off and came out into it and became just essentially encased, intercalated with these red beds. And you can see them kind of wrapping around down here. So here's some of the red beds at the bottom. Here's some of the red beds at the top. There are on this edge here. And so it turns out we're right near the edge of this landslide block. So you had a landslide block come in, and you're at the edge of it, and then the red beds are below it and around it and on this side of it. The previous geologic studies in here tried to make this be basement, like intact Precambrian basement, and it caused a lot of grief in how you draw cross sections and how you interpret the geologic map and where you have to put faults and things like that. And it's just a lot easier to just realize that this was a landslide block. Came off the same mountain, so it has the same stuff in it. Right here, the landslide block is granite. 50 meters that way, the landslide block has meteorite in. And those two rocks are in tight contact, as if it was an original intrusive contact between this granite and the meteorites. And so that mountain had a contact in it, but with granite and meteorite, and that whole piece bearing the contact slid into the basin. For that reason, a lot of people call this cluster of buttes here in Papago Park Contact Hill, because it's got the contact between the meteorite and the granite preserved, but it's not preserved in basement, it's preserved in a landslide block that slid into the basin. So this is the final stop in the South Mountains. It's a good place to end it. And I just want to thank you all for coming on this virtual field trip with me.